Hello again, everybody, and welcome to video 3 in our series, Systems of Linear Inequalities. Today we're going to actually look at solving these things. A system of linear inequalities occurs when multiple linear inequalities are graphed on the same coordinate plane. So we could have 2, 3, 4, however many inequalities we want. In this video, we're going to limit ourselves to just 2 inequalities. The solution region for a system of linear inequalities is the overlapped area of the separate linear inequalities. The solution region can be discrete or continuous, and it may be restricted to certain quadrants. So let's look at an example of that. So let's say I have a solid line here, and my answers are over there. So that's my one inequality graphed. And then we'll say I have another linear inequality going like this, and its solution region is down here. Well, the solution region for this inequality would be the area where both of them overlap. So this would be the solution region for that system. If the solution regions do not overlap, then the system has no solution. So I want to look at that as well. Sorry, I may have just repeated myself. I kind of lost track of my what I was saying there. But let's look at, nonetheless, let's look at when there isn't a solution. So it's pretty obvious if there's not a solution. So here's my one inequality, and there's the solution region. And then let's say we have another inequality here, and its solution regions go on the other side. There is no overlap, meaning there would be no answer. So visually, when there's overlap, that's the solution region. And when there is no overlap, it just means there is no solution. The boundaries of the solution region, now the boundaries are the actual line that you'd be graphing. The boundaries of the solution region of a system of inequalities may or may not be included. So they're not always in the solution region. Depending on which inequality signs and the systems contain. Sorry, on which inequality signs the system contains. So remember, if you have equal to signs, let's just review that real quick. So if I have something like that or something like that, then I have my solid line because I have the equal to. Sorry, my pen's kind of off. If I simply have just the greater than or less than sign, then I'd have my dashed line. And then on top of that, geez, this is really bothering me, my pen. That looks very messy, but whatever, moving on. Beyond that, remember the number system matters too. That if we have, I'll go in blue over here, if we have the x's are the elements of the real numbers and the y's are also part of the real numbers, then we can have a solid line and we can shade like we would here. If we have something like integers, then remember that we have to use a dotted line. So we'd use a dotted line like this, and if we had to shade, then we'd only put dots on the whole number of points. So that is what this last kind of little bit was saying. The second paragraph, you can determine a possible solution from the solution region by checking that it satisfies each inequality in the system. So once we get that visual I've talked about, my overlap, I can choose a point from there and plug it in to both inequalities just to double check it works. The check will be up to you. Intersection points. Use an open dot to show that an intersection point of a system's boundaries is not included in the solution set. An intersection point is not included when the dashed line intersects either another dashed line or a solid line. So I think we should provide a visual of that too, meaning if I have a dashed line and another dashed line, so these would be boundary lines. That would mean any point on this line does not belong in the solution, and including our intersection point, which you just put an open circle like that. So that would mean, I'll draw maybe my solution region here. Now I'll use red maybe for the other one just so it pops a little bit. And I'll get my green out to highlight. So this area here is my solution region, but any dot that would be on that dotted boundary would not be included as an answer. Use a solid dot to show that an intersection point does belong. So I guess this would be one option. You have a dashed and a dashed. The second option is you have a dashed again and a solid. You'd still have an open dot on that. Anytime there's a dashed line involved, that means any point along the dashed line can't be counted. And then the third option would be solid, and then that is the only situation in which our point of intersection is counted. All right, so let's actually try to solve one of these systems of linear inequalities through graphing. So recap again, this is really our introduction. It's just letting you know that we're talking about points. The second part is where you have your pattern or rule that these points will follow. So really, these are just the inequalities themselves. And the third part, that is the number systems. And remember that the inequality sign used and the number system that's in the question, that affects what type of line and shading you do. So in this one, we're dealing with real numbers. So I know I'm going to have a solid line. Or a solid line would be, I guess it might not be a solid line if I don't have the equal to, but solid's a possibility. We're not dotting it. So we're going to have a solid or a dashed line, and we can do our normal shading. And I think we've identified everything we need to identify. So let's actually just start graphing this. So really, there's nothing hard about this. If you were able to do video 2 in the series, you'll be able to do this. We just have to graph 2 inequalities on the same piece of coordinate paper. So my first line, 2x plus y is greater than 6. I'm going to isolate the y because I want to put it in y equals mx plus b form. So we call the line that we're graphing the boundary. So we're going to treat this boundary just like a normal line. So my slope would be -2, and you can interpret that as -2 over 1 if you wish. And we do wish to do that because that's how we'll graph. And then my y-intercept is 6. So my y-intercept being 6 is right up here. My slope being -2 over 1 means I got to go down 2 over 1, so I'd be right there. And then now I'm going to try to draw a nice straight line. I complain every video about drawing these lines with my tablet. It's convenient to have something to blame. It's likely really just more my skills. Anyway, I drew my boundary as a solid line, but now if I look back, I shouldn't have, should I? That should really be a dashed line. So, because I don't have a good erasing function on this software I'm using, I'm just going to make it a green dashed line, okay, everybody? So we are going with a green dashed line. Disregard the red. Sorry about that. And then now the shading. So remember, we want to use that test point for the shading, right? So I'm going to test, and we always are testing 0, 0. And you might not have to do this after a while. You might just get where it goes, or you might just test it in your head, whatever you want to do. So 0 is greater than 6. Is that true? No, that's not. So that means the test point is not in the solution region. Now, so that means my answers are going to be to the right of that line, and I can just shade like this. I like to draw just these lines that are perpendicular to the line that I drew. And I'm able to shade like that because the real number system. Okay, remember that's a green dashed line I have in that one. Okay, so that's my first line graph. So now the second one I'll do in blue, and I'll try not to mess it up. Y is less than or equal to 3. That's already isolated. So remember, that's a horizontal line. So it's going to be a horizontal line that crosses at 3, and I have the equal to sign. So now I can draw my solid line. Okay, now we have to deal with the intersection point. The intersection point, whenever a solid and a dashed meet, you have to use an open circle. So I'll use an open circle here. That just means that intersection point itself is not an answer. And nothing along that green dashed line is an answer as well. I guess I need to shade still. So the y's are less than 3. That means every y value less than 3 would be where I shade. So I'm going to shade down like this. And then again, I'm going to look for my overlapped area. And the overlapped area would be right here. This is where I see my red and my blue. I really should just shade that in with purple, shouldn't I, you art people out there? Anyway, that would be my solution region for this system. Often you're asked just to provide a sample answer. So my sample answer, and reason I ask that is just to make sure you know what actually you found. I just picked some point that would lie in that region. So I don't know if they'll see the yellow, but if I pick this point here, which would be 4 and 1, that would be a sample answer. If I wanted, I could check it. I would just plug that x and y into each of my inequalities and then see if the resulting expression is true. So you'd have to see, well, why don't I just show you? Why talk about it? Let's show it. I'll use yellow. I'm starting to run out of room. But I'll check it down here. This is very messy. I'll do a less messy job next time. 2 times 4 plus 1 is greater than 6. That's 8 plus 1 is greater than 6. 9 is greater than 6. So that's true. It's a solution for that one. If I use my other line, which is y is less than or equal to 3, well, my y value is 1, less than or equal to 3. Is that true? Yes, it's true. That means that point definitely works for both inequalities. All right, so that's how you do it. It's a little bit more work than graphing one, but truly it's not too much. Okay, so I need another crack at that to do a nicer job and not make a mistake either with that dashed line. Oh well. Okay, so again, here are my inequalities. I should really make a notice to myself right now, or make a sign to myself. That one is going to be a dashed line. Why? Because it has just a less than sign. There's no equal to part. And you can see that in the back part, we're dealing with real numbers still. So I can do my nice lazy shading. Okay, so I'll go red first again. Y minus x is less than 2. I'm going to isolate that y. X plus 2. So my m is 1, but I want to interpret that as 1 over 1. And my y-intercept is positive 2. Okay, and again, the line we're going to be drawing here, we call that the boundary line. So my y-intercept is 2. My slope says go up 1 over 1. I'm there. Double check. Yes, I'm drawing a dashed line. Don't mess that up like I do. Okay, insert complaint about line like I always do. There we go. There's my dashed line. Okay, so now the shading. I'll have to test that real quick. And again, I'm always choosing my test point to be 0 and 0 because that's just easiest. And I can check that down here real quick. 0 minus 0 is less than 2. 0 is less than 2. That is true, meaning that green point lies in the solution region. So, and we're dealing with real numbers, so I can just do my lazy shading. Now remember, what I should really do is I should really be shading everything in. Like I should actually be coloring it in like this. Okay, that just gets kind of messy, but we can do that, and I guess it's not so bad on this one. I'm using some different colors, but if you don't feel like if you don't want to do this and just draw the lines like I do usually, that's fine too. I find that those lines kind of make a nice, neat picture. Okay, so line 2 now. X plus y is greater or equal to 0. So this will be a solid line because I have that equal to, so I'll subtract x. Y is greater or equal to negative x. So I've got y isolated, so now my slope is going to be negative 1 or negative 1 over 1. My b value, don't see, so it's a 0. All right, so just in case you forgot that. So my 0 is my origin right there. It says I'm going to go down 1 over 1, which is right there. I get to draw a solid line this time. Look how hard I have to concentrate. I get quiet when I'm drawing these. There's my line, and then now I have to figure out, I have to test to see is that 0, 0 point in the solution region or not. And you can see, well, there's a bit of an issue. It passes through there. So if your test point is actually on the line, that's not going to tell you should you shade above or below. So I'll pick something different. This time when I test, I'll pick 1 and 0. All right, 1 and 0, which is right over here. Sorry, right here. That is definitely above the line, right above that blue line. So that'll do the job. So 1 plus 0 is greater than 0. 1 is either greater or equal to 0. That is true, meaning that green point is in the solution region. So I'll go back to doing this. The other thing now we have to talk about is that intersection point. It's a dashed line, meaning a solid, so that means this intersection point right here, that point does not belong in the solution region. Anything along the dashed line doesn't count. Okay, so you can likely see for yourself that this, I'll put some green in here. This is my solution region, this kind of triangle shape that I'm getting. So a sample answer. Anything from that region, and I actually can use my test point. My test point happens to be 1, so there would be my sample answer as well in case that was asked. So really, we have a few steps here. Our first step would be to graph and shade each individual. And then the second part is really just determining the region, solution region. Lots of little steps with this, but I think overall you guys will do just fine. Let's do one more. You can see our equations or inequalities are progressively getting to be more numbers in them. They're not anything crazy though, people. So here's my first inequality. Here's my second inequality. I can see that they both have equal to's in them, so I don't have to worry about my mistake where I just automatically draw solid lines all the time. Like that is something I honestly do. I default to draw those solid lines. So I bet there's a few people out there, as in you guys, that'll do the same thing. So just make sure you check that out. Okay, so let's begin. We're going to graph this boundary, which is the line. And it's called a boundary because it separates the answers from the non-answers. So I want to isolate my y, so I got to move this over. Remember, we have to change the direction of the inequality sign if we multiply or divide by negative. Good thing I brought this up, everybody, because we are, I'll highlight this, we are dividing by negative. So that means I simply need to change the direction of the sign, and I went over that in the previous video as to why, so I won't do that again here. Not a big deal. You never have to add or take away the equal to part. You simply flip the direction of that greater than or less than sign. Slope is that. Y-intercept is that. So there's -4. I have to go up 4 and over 3. So 1, 2, 3, 4, and over 3. Right there. Sorry, you might hear some sounds in the background. That's my computer. When I receive an email, I get a little sound going off there. Okay, so there's my first line. It's solid because it was as equal to, and I get to shade in my kind of lazy way because they're real numbers. So I need to determine though, am I going to shade above or below that line? So 0, 0 can be back in play because that's not on the line. So I'll test it real quick. 4 times 0, and you can do this in your head. You don't need to show this work as long as you know what you're doing. 0 minus 0 is less than or equal to 12. 0 is less than or equal to 12. Is that true? Yes, it is, meaning that green point is in the solution region. So I'm going to go back to just drawing my lines because I like that the most. But if you want to get into your shading, channel your inner child like it's coloring or something and do a nice job of coloring that, that would actually be better, but I'm not going to do that. This takes a little while. Okay, so there's my first inequality. Again, I want to make sure we know this. The boundary, we call the line itself the boundary, everybody. Okay, so if I ever use that language, just so you know what I'm talking about. Okay, my second inequality in this system, 3x plus 5y is less than or equal to 15. Same process, everyone. Divide by 5. It's a positive 5 this time, so I do not need to flip my inequality sign. Okay, there's my slope, there's my y-intercept. So there's my first point. Now down 3, 1, 2, 3 over 5, 1, 2, 3, 4, 5. So you can see here that this happens to be intercepts both times. So remember, there is another way you can graph. You can graph via the intercepts, the x-y intercepts. I don't. I mean, I can. I just don't usually do it that way. Again, now I got to draw a solid line because I had an equal to in the question. I can use a solid line or a solid dot at this intersection point. This intersection point would count as an answer because both these are solid lines. I need to test to see where I should shade. The 0, 0 can be used again because it's not on that blue line. So 3 times 0 plus 5 times 0 is less than or equal to 15. So those work out to 0. 0 is less than or equal to 15. That's true. So that means, again, that green dot is in the solution region. And then I can draw, whoa, let's go blue. I'll draw my lines perpendicular. Okay, and then if you want, I always like to kind of just go over it again and just highlight what my solution region will be. So it's going to be here. Kind of go around it first. So that green area would be the solution region. That is where there's an overlap. A sample solution, if you're asked, could be anywhere. So I'll just pick right here, -1 and +1. All right. So that is how you graph a system. What can be confusing is the type of line, the shading, the intersection point. Really, it's not difficult. It's nice to write those things down and just keep double checking back when you are working through your assignment. You'll get it down over time. Okay, I hope that helped. If it didn't, talk to your teacher or talk to me. Have a great night, everybody.